Good morning, everyone. My name is Chi-Feng, and I'm currently an associate professor at the Department of Material Science and Engineering at National University. And I'm very honored to be invited by Professor Terry Ono to talk about our recent results on the long-range interlayer chiral exchange. Unfortunately, I won't be able to attend this very prestigious Magnetic Society of Japan annual conference in person, so I have to show you our results this way. So here's outline my talk. I'll give you a very brief introduction of what interlayer DMI is and how we observe this kind of effect, and also the tailoring of interlayer DMI by a so-called azimuthal symmetry engineering technique. So we already know about RKKY interaction, which is omniscient in many MTJ devices. And for this kind of exchange coupling, the two magnetic layers are coupled in either a linear or collinear configuration, but they have this kind of oscillatory, damped oscillatory behavior for the exchange coupling strength. And was first reported by Parkin that the Ruthenian spacer thickness can change this coupling in an oscillatory way, which are already being used in many MRAM devices. And for the Dzyaloshinskii-Moriya interaction, or DMI for short, the local spins are also mediated by conduction electron. But in this case, we need another non-magnetic atom with spin-orbit coupling to introduce this symmetry breaking. And a typical form of this DMI Hamiltonian is presented like this. So we have the cross product term here, and then this result will have inner product with the DMI D vector. An illustrative way is something like this, that in a normal metal ferromagnetic bilayer structure, the spins or magnetization in the ferromagnetic layers will be affected by the spin orbit coupling coming from this normal metal layer. And then the two magnetization will then have this non-collinear configuration. So what we just saw is what we call the conventional interfacial DMI, and this is typically achieved by having this kind of Z direction symmetry breaking. And as an example shown over here, if a ferromagnetic layer is sandwiched between two normal metal layers, and if the two normal metal layers have like different materials or different thickness or different structure, and sometimes you will also see this normal metal layer being replaced by oxide layer. So in this kind of symmetry broken structure, then the ferromagnetic layer within will have this experience this interfacial Dzyaloshinskii-Moriya interaction. And this can be observed in, for instance, platinum cobalt iridium or iridium cobalt platinum trilayer structures. And apparently, this inversion asymmetry can be manipulated by changing the stacking order. However, if you can play with the lateral symmetry breaking, in this case, two ferromagnetic layers, they are separated by a normal metal layer. And if this normal metal layer sort of having a lateral symmetry breaking, either in structure or in compositions, it is possible to rotate this symmetry breaking vector to in plane. And this is typically achieved by, at least in our group, by oblique angle deposition. That is by stopping the rotation of the substrate or sample holder during deposition, and then you have an angled deposition of the magnetic layers or the buffer layers, and to create lateral symmetry breaking in the thin film. Some of the groups reported that if you use the regular, rotation during the deposition, but at the same time, if you apply an in-plane field during the deposition, that will also give you a symmetry breaking. And later on, some people say that this can also give you the interlayer DMI. But in our case, we found that the wedge deposition is more powerful and more successfully deliver the results that we want. And so we're going to focus on this kind of oblique angle deposition technique, or wedge deposition technique. And some of the famous or popular configurations for showing this kind of interlayer DMI effect is either using the double PMA structure. So this can be synthetic ferromagnetic layer or synthetic anti-ferromagnetic layers, or using the orthogonal type T structure. So at the beginning, I'm going to show you the results coming from the type T approach, which is much simpler because we just have a one in-plane magnetization and the other having perpendicular magnetic anisotropy. And the effective field can be much easier to be captured. And note that in this kind of structure, naturally, it's already having this kind of 90 degrees angle of the two layers. So it will be much easier to observe the DMI effect, since this the DMI is related to the cross product of the two ferromagnetic layers. So for the second part, I'm going to show you how we generate and detect interlayer DMI and its importance in realizing current-induced field free switching. So the Hamiltonian of the two interlayer DMI couple magnets is having this kind of form, like we just show in the interfacial DMI case. So ideally, it's the same, except that for the M1 and M2 here, those are the magnetizations of the two layers. And under the type T configuration, and if the M1 and M2 are one having perpendicular anisotropy, the other having in-plane anisotropy, the effective fields coming from this Hamiltonian acting upon the two layers will be having a form like this. So for the PMA layer, it is experiencing a magnetic field or effective field coming from the in-plane layer. So if the D vector and the in-plane magnetization layers are having 90 degrees orientations, then the DMI effective field will be maximized, and it is acting upon the PMA layer. And reciprocally, you should be able to observe the effective field coming from the PMA layer acting on the in-plane layer. So in this talk, I'm not going to show you our reciprocal effect observation, but indeed, we could observe this kind of effect. So depending on which layer you are characterizing, you should be able to see the reciprocal effect if you're detecting the other. But nevertheless, if we compare this to the interfacial DMI case, again, this can the chirality of the D can be tuned by interfacial engineering or layer stack engineering, and as will be shown in the later part, the direction of D can be engineered. Okay, so how we generate the interlayer DMI? We introduce this very simple structure. So the in-plane magnetic layer is simply in-plane cobalt or iron boron, 2 nanometer thick. And on top of this structure is a platinum cobalt platinum sandwich structure, which is very typical to introduce PMA for the cobalt layer. And the platinum here serves as a spacer in between cobalt and cobalt boron. And at the same time, this is illustrated as the interlayer DMI mediation layer. Okay, so platinum provides high spin-orbit coupling, and it can also help us generate PMA in the cobalt layer. So we have two advantages. And how we introduce the symmetry breaking in this case, we use wedge deposition of the cobalt and boron layer. So during the deposition of the cobalt and boron layer, the rotation is stopped, and then we have a specific angle to deposit cobalt iron boron relative to the XY plane of the thin film. So in this case, for example, this is the XY axis, and this is the film plane, and the cobalt iron boron target, the atom flow is coming into the film plane like with 60 degrees away from the x-axis. So in this case, according to the third Moriya rule, the D vector direction should be 90 degrees away from the symmetry breaking plane. Therefore, the D direction should be 150 degrees away from the x-axis. So how we measure this kind of effect? We first pattern the thin films into whole bar devices, and we use anomalous Hall effect to capture the magnetization signal coming from the perpendicularly magnetized layer, which is the cobalt layer that I just mentioned. And for output station, we'll apply an in-plane field in the first place, and that is with a fixed direction to point the cobalt boron layer, in-plane cobalt boron along some certain direction, and then we sweep the outer plane magnetic field to capture the outer plane hysteresis loop of the cobalt layer. That is recorded by the anomalous Hall effect of this Hall device. And by changing the in-plane field direction, we will see an obvious shift in terms of this overall hysteresis loop for the cobalt layer, which means that the outer plane hysteresis loop is being shifted by an effective field coming from the in-plane cobalt boron layer. And this is consistent with the interlayer DMI scenario. So if we plot this H offset, which is the effective field coming from the in-plane layer, by changing or as a function of the in-plane field that we apply, that is the cobalt boron magnetization direction, we'll see this kind of sinusoidal dependence. And that is exactly related to the D cross M that we just mentioned earlier. So this sinusoidal dependence confers the anti-symmetric interaction or interlayer DMI. And what's more important is from this data set, we can extract the strength of DMI effective field. And in this case, the DMI effective field is about 40 Oersted. And from the sinusoidal behavior, we can also identify the DMI angle, which is about 150 degrees away from the x direction. So that is consistent with what we just mentioned earlier, that this D direction is orthogonal to this a wedge deposition angle. So by using this effective field, we should be able to generate field-free current-induced switching. And the idea is that if we can use current to switch the in-plane magnetization, which is cobalt boron in this case, then we should be able to simultaneously switch the perpendicularly magnetized cobalt layer, because those two layers are coupled to each other through interlayer DMI. So the idea is that if we have a D direction pointing, for instance, in this case, along the x minus x direction, and if we apply current along the x direction, and that will generate, for instance, an SOT or effective field acting upon the in-plane layer. And if the in-plane layer is switched, then at the same time, the DMI effective field will assist the outer plane layer to switch, as long as this DMI effective field is greater than the coercivity of the outer plane magnetic field, outer plane magnetic layer. So what's more important is that on the same substrates, since we prepare the wedge deposition across this substrate, the D vector of this substrate or the thin film will be the same across this wafer. However, we can pattern devices with different orientations on top of this wafer. So if we have 45-degree device and 135-degree device, although their D directions are all pointing along the same direction on the wafer, but the relative orientation of this D vector towards the current direction will be different. So in these two cases, if you switch the magnetization of the in-plane layer, and IMA in this case, the perpendicular layer will switch accordingly through interlayer DMI. However, since the direction of D and I are different in these two cases, we will observe opposite polarity of the PMA layer switching. So the key point is that the relative angle between the current and the D vector will dictate the switching polarity for the perpendicular layer. And keep in mind that for the in-plane layer, here are the switching results, that the in-plane layer, they have the same polarity because they are not being affected by the DMI effective fields. The switching of the in-plane layer is solely governed by the SOT or the Oersted field or whatever effective field that is going to switch the in-plane layer. However, the PMA case, the cobalt layer switching, you can see that the blue data here for these two devices with different orientations, they have the opposite polarities. This is because the D and I, the D direction and the current directions are different in these two cases. So this is the confirmation of that the switching indeed is coming from the in-plane layer, because they have a very similar switching current or switching current densities, but the polarity for the in-plane layer switching is not being affected by DMI, but the perpendicular direction will be affected by the DMI. So this is the first observation, or at least the interpretation is based on interlayer DMI and coherent switching of the two layers. So for the first part, I believe I show you how we use the wedge deposition technique or oblique angle deposition technique to generate in-plane symmetry breaking, and that will give us, a suitable amount of interlayer DMI and effective field, and we can quantify that by the field scan measurements. And the sinusoidal behavior that we observed is consistent with the interlayer DMI explanation. And we also demonstrate coherent switching of both the in-plane and out-plane layer by using this kind of RL-DMI device. And this is the switching of the PML layer is due to the switching of the in-plane layer. And then because those two are coupled through the interlayer DMI, so they can switch coherently. So for the next part, I'm going to show you how we further optimize this kind of IL-DMI switching by playing with the deposition combinations or different sequence of thin film deposition. And we'll show you that not only in the type T devices, but also in the synthetic antiferromagnetic layer devices, we can demonstrate successful and almost 100% field-free current-induced switching. And for the last part, to show you the device-to-device inhomogeneity can be resolved by a certain technique called the self-counter wedge deposition. So this oblique angle deposition, like I just mentioned earlier, has been already utilized in many different areas of research. And for us, spintronics people, for instance, we've already seen that it can be used to generate field-free SOD switching. For instance, in this case, they show that the slanted, this oblique column growth of chromium is probably the key to generate field-free switching in this chromium covalent boron MgO device. And in our case, we found that since the platinum layer sandwich to sandwich the cobalt layer, we have two layers of that. So it is possible that we can use multiple OADs, multiple oblique angle depositions, to play with the DMI strength or even the directions across these cobalt and cobalt boron layers. So we want to show that if the D wedge directional relationship provide any insights into the nature of interlayer DMI. So similar to what I just showed earlier, the structure is also having cobalt boron as the in-plane layer and platinum cobalt platinum as the PMA layer. But now the structure is reversed, which allows us to play with more, like say, we have more freedom to play with the oblique angle depositions. And again, we pattern that into whole bar devices to quantify the so-called effective fields coming from the in-plane layers. So again, here is the out-plane hysteresis loops of the cobalt layer. And if we change the in-plane field direction, that is by fixing the cobalt and boron layer along different directions, we observe shifts in terms of the effective field coming from the cobalt and boron layer, acting upon the cobalt layer. What's more important is that since we have two platinum layers, if we wedge different platinum layers, we'll see not only the magnitudes will change, but also the sign of the DMI could be changed by the wedge engineering. So if we summarize our different combination of wedge engineering, we can see that not only the magnitude can be changed, but also the sign. Especially for this case, if we use the same direction of wedge deposition for the top platinum layer, same as the bottom one, we can change the sign, which means that if we use the opposite sign for the top and the bottom platinum layers during the deposition step, we should be able to further enhance the DMI, and that is exactly what we observed. So this sort of some rules that we can use to engineer the interlayer DMI strength of the overall heterostructure. So again, the third Moriya rule is followed, is obeyed. So no big difference from the previous case. But what we showed is that the buffer layer contribute to much higher HDMI. The bottom one typically give you larger DMI, and the top one give you lower. But if you can change the direction of the wedge direction, you can further enhance the bottom contribution. So overall, the DMI's value of multiple wedge layers is the sum of individual symmetry breaking factors. And we can observe the same thing in the SAP structure. So I won't go into details, but anyway, right now we have 3 layers of platinums. So which means that we have even more degrees of freedom to play with the magnitude and the sign of DMI. And indeed, the sum rules still apply in this SAP structure. And again, we can observe this kind of effective fields coming from the SAP structure. So what could be the microscopic origin? Earlier theoretical work showed that they assume if the system has some coordinate shifts in the normal metal layer, then it is possible to create, this kind of unbalanced triangles in the 3-side model. So we call this a shifted Levy-Furth model with a very simple. So we originally, as we can see earlier in the interfacial cases, 3-side model, but now we have 2 triangles, right? Because we are considering both the top and the bottom cobalt atoms, and in between we have the spacer platinum layers, and the platinum atoms is illustrated here. So we have 2 triangles. So as long as the triangle areas for these 2 are not equal to each other, then we will have a sum, a net value of the D vector, and that will give you a finite value or a certain direction of D vector. But without this kind of atomic displacements, delta 1 and delta 2, then D1 and D2 will cancel out with each other. So the sum will be 0. So we start to believe that this is probably due to, so the reason why we can see this kind of sum rule is due to during the wedge deposition, this displacement of the atoms is created by the templating and the shadowing effect from this wedge deposition. However, right now we don't have the microscopic evidence for verifying this assumption or this claim. So we're encouraged. So we encourage the theorists or microscopic scientists to work on this and to give us a direct evidence to show us that this kind of atomic shifts is indeed can be fit into this Levy-Furth model, and then explain our observation of the sum rule of the interlayer DMI. But nevertheless, in terms of phenomenology, this model gives us very nice qualitative agreement in terms of the model calculation. And if we compare to the experimental result, as you can see over here, the combination of displacement, again, agree with this kind of type of wedge. So even their relative magnitudes are very consistent with what we observe in terms of the magnitudes of the effective field being probed, experimentally. So this reverse OAD enables the oppositely slanted column structure, probably related to what we observe over here, to change the sign of the D vector. And what's more important for application is the field-free switching behavior. So we demonstrated that in both type T and the SAP structure in these kind of optimized devices, they all show very nice switching behavior. And the switching will disappear when the current pulse is perpendicular to the D direction, because in that case there is no symmetry breaking mechanism. So when the current pulse is parallel to the D vector, typically you observe the largest switching, the largest portion of switching. And due to the high DMI effective field, the switching percentage is also very high. So if you use field to switch and if you use current to switch, and the switching percentage are very close to each other. And the switching mechanism for the SAP case, I won't go into details, but it is also related to the reciprocal effective field effects. And if you're interested in the details, can refer to some of the earlier works from different research groups. But anyway, one of the important issues that we want to address in this kind of wedge deposition prepare samples is that if you're dealing with large area deposition, then it is possible to have a large thickness variation across the wafer, because for a single device, the thickness difference is very, very small, very, very minute. It is impossible to be the source of interlayer DMI. But if you across the wafer, then we will have this very huge thickness variation. And how to eliminate that kind of effect? First, we observe that in this kind of structure, we have 3 platinum layers to play with. Second, if we can introduce the so-called self-counter wedge, that is within one platinum layer, we just use 2 different directions of wedge deposition, then it is possible to, within a single layer, we already eliminate this kind of thickness variation. So that can further mitigate this overall thickness variation when we have a full wedge deposition. And in this case, like I talked to my students, I would like to say this is more like artificial 2D materials, okay? Because within 1 nanometer of the platinum layer, we have 2 different like wedge deposition and probably 2 different like column growth directions. So if this is the case, we hope that some other experimentalists will help us image out this kind of a self-counter wedge structure. And at the same time, this still retains the symmetry breaking along the lateral direction. So ideally, the interlayer DMI should still be kept. And indeed, we observe that if we use the self-counter wedge, the resistivity variation is much smaller while compared to the regular case. And what's more important is that the switching, the current-induced switching behavior is retained, and we can have a very, very stable switching percentage. And at the same time, the variation of the switching current across the wafer, this is a 3-inch wafer, is also less while compared to the case without this kind of self-counter wedge engineering. So it is advantageous for practical integration, especially for larger area of wafer. And again, the homogeneous switching current and polarity in self-counter wedge system is important, and it's an indication that this kind of approach can mitigate the thickness variation issue if you use wedge deposition in your samples. So last, I want to summarize my work. So I believe I show you that the tunable interlayer DMI can be done by the OAD control. You can do different OADs to generate the subcircuit sum rules for the interlayer DMI. And that kind of sum rule sort of give us hint on the microscopic urge. It's probably related to the Levy-Furt 3-site model. But we still need a direct microstructure confirmation, which is still lacking at this moment. However, in terms of engineering, by using this self-counter wedge, we believe that it can mitigate this thickness variation issue and give us a better device-to-device homogeneity, not only in terms of the thickness, but also resistivity and also the uniform switching behavior across the wafer. So at last, I want to acknowledge my students, especially Dr. Yu-Hao Huang, for his contribution to all this interlayer DMI works, and also other students, Han Ruixu, and also Dr. Chen Yuhu for their contributions in this work. So if you are interested in more details, please refer to this nanoletters work published earlier this year. And thank you for your attention. If you have questions, unfortunately, I'm not in the scene, but you are feel free to email me to get more details. Thank you for your attention.